Okay, we're now ready to begin our study of calculus. And I talked previously that there's two main branches of calculus: differential calculus, or the study of derivatives, and integral calculus, the study of integrals. And these two branches stem from those two main problems in calculus: the tangent line problem and the area problem. But before we talk about either one of those branches of calculus, we have to talk about a very, very important topic, and that is the limit. So the topic that we're currently going to be looking at is limits. And so notation-wise, the limit as x approaches c of f of x is equal to L. So first of all, this limit here, this is what's called an operator. This is a mathematical operator. It works on something or operates on something. So just writing LIM with a little x arrow c. That's the limit as x approaches c. By itself, it doesn't mean anything. By itself, it's like saying, what is that equal to? Well, an empty square root is not equal to anything. It's just a symbol. It's an operator. It needs something to operate on. So just like with a square root symbol, you would need a number under there for it to be equal to something. Well, same thing. The limit as x approaches c, well, it's operating on, it's basically operating on some function, f of x. Okay, so let me erase this because we're going to need some more room here. So the limit as x approaches c of f of x is equal to L. Now, this L, this is a number. This is actually, it's a y value. So let's start with a generic function. Let's say we have like I'm only looking at quadrant 1, but that's we don't need to only work in quadrant 1. Let's say we have this parabola. So there's our function, f of x. So let's say the limit as x approaches c, which means we're looking at x values close to some given number. We'll call that c. And so what this L is, it's the y value that points on the function are approaching, or that's the y value, the function values are approaching as x values get closer and closer to c. So as the x values do this from both sides, as the x values do this, what do the y values do? And that's that number L. And so here we have a continuous function. So it looks like, well, there's a point on the function here, and this over here is f of c. So as the x values, let's go back to green, as the x values are doing this, as the x values are getting close to this number c, the points on the graph are getting closer and closer to this red point. And that red point is the point c, comma, f of c. So in this particular case, as the x values are getting closer and closer to c, the y values are getting closer and closer to f of c. We don't care what's happening at the point. We're concerned with the values that the function is approaching as the x values, or the input. So what are the output values getting close to as the inputs are getting closer and closer to c? Now this is one specific case where we have a continuous function, so the point, so if we look at as the x values get closer and closer to c, points on the function are getting closer and closer to this red point. Now it's not necessarily true that that point is going to be a point on the function, on the graph of the function. So let's look, for example, at the function, I don't know, f of x equals x squared minus 4 divided by x minus 2. What I want to examine here is the limit as x approaches 2 of f of x. The limit as x approaches 2 of x squared minus 4 divided by x minus 2. Now, if we were to graph f of x, if we were to graph this function f of x, what does it look like? Well, it's not as complicated as it looks, because if we factor this difference of squares, we factor x squared minus 4, we have x plus 2 times x minus 2. Then on the bottom, we have an x minus 2. So it looks like the x minus 2's cancel, and we're left with just x plus 2. But this function that we started with, f of x, is not equal to the function x plus 2. It's almost equal to, but if we look at these two functions, f of x equals x squared minus 4 over x minus 2, and that's simplified to x plus 2. So let's say we have another function, g of x, and we'll call that g of x as x plus 2. Well, are those two functions the same? Well, for them to be the same, they have to have the exact same points, the exact same y values for any x value. So let's say we plug in a value for x, and we look at f of x, and we look at g of x. Well, if x is equal to 1, what do we get? Well, f of 1, if we plug in 1 here, it's 1 squared, or 1 minus 4. And on the bottom, we have a 1 minus 2. Okay, so f of 1 would be a negative 3 on top and a negative 1 on the bottom. So that would give us positive 3. And if we plug in 1 to g of x, 1 plus 2 is also equal to 3. If we plug in 0, 0 minus 4, 0 minus 2, negative 4 divided by negative 2 is 2. If we plug in 0 to the g of x function, g of 0, 0 plus 2 is also 2. Now, this always will be the case that f of x and g of x will be equal to each other, except what happens if we plug in 2 for x? Well, if we plug in 2 for x, in the g of x function, 2 plus 2 is equal to 4, but in the f of x function, we get 2 squared, which is 4, so 4 minus 4 on top, and we get 2 minus 2 on the bottom, so we get, so f of 2 is equal to 0 over 0. Well, that's not 4. And that's not even a defined number. You can't divide by 0. You can't divide anything by 0, not even 0. So 0 over 0 is undefined. Undefined. So that's the one value where these two differ. So back up here, f of x equals x squared minus 4 divided by x minus 2, and that simplifies to x plus 2, but we have to add one caveat to that. Let's do that. We'd have to say for x not equal to 2. X cannot equal 2. So we know the graph of x plus 2 is a straight line, but when we graph f of x, it's actually a straight line with a slope of 1 and a y-intercept of 2, but when x is equal to 2, what happens is there's a hole in the graph. So when x is equal to 2, there's a hole up here at 4, at the point 2, 4. So that hole, the location of that hole is the point 2, 4. So what does that tell us? That tells us that f of 2 is undefined. There's no point on the graph when x is equal to 2, but the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, the limit is defined. We don't care about what happens, and that's the whole point of this limit. We don't care about what happens when x is equal to 2. We care about what happens when x is getting infinitely close to 2. So the limit is the location, or the y value of the location, the y value of the point that the function is approaching, is getting closer to. So as the x values get closer and closer to 2, the y values are getting closer and closer to 4. And this is the whole point of the limit here. It's as x is getting close to 2, what is the behavior of the y values? And so, even though the function is not defined when x is equal to 2, the limit is. So the limit is the y value of the point that the function is getting, that the graph of the function is getting closer and closer to as x is approaching this number. So exactly at x equals 2, the function is undefined. But for any point that's not, for any point with an x value that's not 2, the function is defined. So that means the limit, in this case, the limit is defined. So, first example, this continuous function. The function is defined at x equals c, and also the limit is defined for x approaching c. Okay, down here, the function's not defined, but the limit is. Now, there are other cases where the limit is not defined, where the limit, where there's no specific point on the graph, or there's no specific point in the xy plane that the points on the graph are approaching. Let's say, for example, and let's go with f of x is equal to the absolute value of x minus 1 divided by, let's say x minus 3, divided by x minus 3. Well, without the absolute value bars, x minus 3 over x minus 3 is equal to 1, except in the case that x is equal to 3, because f of 3 is undefined, because if you plug in 3 for x, again, you get 0 over 0. But for any number that's not 3, it's okay. You could plug in any number that's not 3 because you'll get something other than 0 on the bottom. And now what this graph looks like, well, any number over itself is equal to 1. So for any number you plug in, you're going to get the same number on the top as you do on the bottom, except you may get a positive or a negative 1. So for numbers bigger than 3, if x is bigger than 3, the top is positive, the bottom is positive, and they're the same number. So for any number you plug in bigger than 3, you get 1. So the graph looks something like this. You can't plug in 3, so 3 doesn't work. There's a hole at 3. Now, if you plug in any number less than 3, like if you plugged in a 2, you get the absolute value of 2 minus 1, or 2 minus 3, divided by 2 minus 3, which means the top would be a positive 2, and the bottom would be the top would be a positive 1, and the bottom would be a negative 1. So any number over itself, where 1 is positive, 1 is negative, will give you a negative 1. Okay, so over here on the left, this type of discontinuity is a hole. It's a single point removed from the graph, and holes do not affect limits. This type of discontinuity on the right, this is a jump discontinuity. This does affect limits. So if we look at, in this case, if we look at the limit, well, first of all, f of 3 is undefined, because if you plug in 3, you get 0 over 0. But the limit as x is approaching 3 of the absolute value of x minus 3 over x minus 3, well, this is also, in this case, undefined. Because the limit, for the limit to exist, for this number L to exist, so remember we're doing the limit as x approaches c of f of x equals some number L. L is one specific number. So the only way that this limit exists is if it's equal to one specific number, which means there has to be one single point on the graph that the graph is approaching as x approaches some number. So as if we look at this graph, as x is getting closer to 3 from above, like 3.1, 3.01, 3.001, and so on, getting closer and closer to 3, all the y values of all of these points are all equal to 1. So coming from the right, coming from above, the points on the graph are approaching this point. I mean, in this case, it's a hole, but it's still a point. It's still a location. But coming from this direction, all the points on the graph are down here. So like so when x is 2.9, 2.99, 2.999, getting closer and closer to 3 from below, the y values are all negative 1. So we have two different locations that the points on the graph are approaching. If you're coming from above, the points on the graph are approaching this hole. And if you're coming from below, the points on the graph are approaching this hole. So we have two different values for L. The limit can't be equal to two different numbers. So in this case, we say the limit is undefined. And that's because the behavior of the graph coming from the right and the behavior of the graph coming from the left are different. But if this was anything other than 3, we would be fine. If we had the limit as x approaches 2 of this function, or we had the limit as x approaches 4 of this function, we're fine, because as the x values are approaching 2, so if 2 is here and 4 is here. So as the x values approach 2, all the y values are down here at negative 1. And again, on the right, as the x values are getting close to 4, the y values of all of these points are all positive 1. So this limit would be equal to positive 1. So the only issue is exactly when x is equal to 3. So when you have a jump discontinuity, and later on in this chapter, we'll talk about the different types of discontinuities more formally, but there's basically 3 types: holes, jumps, and asymptotes. This first type, a hole, does not affect the limit. The limit is still defined. Even though the function is not defined, the limit is still defined when the x values approach a location where there's a hole. With a jump, the limit is not defined because you have a different limit value from the right as you do from the left. Now, we'll later talk about one-sided limits. So if you look at the limit only coming from above, like only the green one, we can talk about that limit because all of these points, if we ignore the left-hand side of this graph, and all of these points on the right are all approaching this one location, this hole. Same thing with the left. If you're only looking at numbers below 3, then the one-sided limit coming from the left, well, that also works because they're all approaching this point. The third type of discontinuity are vertical asymptotes. Now, with a vertical asymptote, that's also a situation where the function does not exist. So let's look at the function, I don't know, f of x equals the tangent of x. And the tangent function looks something like, let's see, we have a graph. And the tangent function, which is equal to sine over cosine, so there are places where the tangent function is undefined, sine over cosine. It's undefined when the denominator is 0. So anytime that the cosine value is 0, you have an issue. You have an issue with this being undefined. And that happens at pi over 2. And it happens at negative pi over 2. I'm just going to draw one cycle of the tangent function. It happens also at 3 pi over 2 and 5 pi over 2 and 7 pi over 2 and so on. But at pi over 2, we have a vertical asymptote. So let's actually draw one cycle of the tangent function, and the tangent function looks like this. So if we were to look at the limit as, let's say, x approaches 0 of the tangent of x, well, that's fine. As the x values are approaching 0, these points on the function are also approaching 0. So as x gets closer and closer to 0, the values of tangent of x are also getting closer and closer to 0. Or if we wanted to say the limit as x approaches pi over 4 of the tangent of x. Well, that's also defined because the tangent of pi over 4 is equal to 1. And at pi over 4, there's no issue with the graph. The graph is continuous. There's no holes. There's no jumps. There's no asymptotes. There's no discontinuities is equal to 1. But if we look at the limit, let me change this to blue. If we look at the limit as x approaches pi over 2 of the tangent of x, well, there's going to be another tangent function here. So as the x values are getting closer and closer to pi over 2, what are the y values doing? Well, they're not getting closer to any one specific number. They are increasing without bound on one side and decreasing without bound on the other. Now, the fact that they're two different directions doesn't matter. The fact that they're going to infinity, they're getting infinitely large, well, that's the issue. Now, again, back up here. For the limit as x approaches c of f of x to equal L, for the limit to be defined, L has to be one specific number. Infinity is not a number. Infinity is an idea. It's an adjective. It's like blue or or round. It's a concept. It's not a number. So L cannot be infinity. And since as the x values approach pi over 2, the values of the tangent function increase without bound or go to infinity, we would say this is undefined. So when x is equal to c, if there is a jump or if there's a vertical asymptote, the limit will be undefined. If there's a jump, that means the behavior from the two different directions will be different. And if there's a vertical asymptote, the y values are not approaching a specific number. They are going to infinity or negative infinity or both. Okay, so that's basically like a brief overview of limits. It's not a concrete topic, and it's not terribly difficult once you wrap your mind around it. The important thing is we do not care what happens on the function at x equals c, where c is just some x value that's chosen. We care about what the function is doing for x values that are getting closer and closer to c without ever actually getting to c. Okay, so in the next videos, I'll be dealing with more specific examples of different situations where we're working with limits. Now, limits are very, very important. They're going to be coming back later over and over and over in the course. Basically, anytime we need to, establish a formula or prove something in calculus, we always use limits. And when we get into, when we start with our exploration of differential calculus, or the study of the derivative, well, we define the derivative using limits, and we establish every derivative formula also using limits. So this is not a topic you're going to see and then leave behind when we move on to the next topic. This is going to permeate the whole study of calculus through calculus 2, through calculus 3. So it's a very important foundational topic. Okay.